In this video, we are going to learn how to interpret and convert numbers from different bases into decimal, base 10. All of our lives we've been using base 10, which has 10 digits, 0 through 9, but now we know about different bases. We are going to need a notation to distinguish between numbers from different bases. If I show you the number 1, 1, you would normally presume that is the number 11 in base 10. However, if it is in binary or base 2, it would actually be the equivalent of our number 3. If it is in hexadecimal or base 16, it would be the equivalent of our 17. Moving forward, we will use subscripts to indicate the base of a number. If a number does not have a subscript or any other mention of its base, then you may assume that it is base 10. Before we learn how to do conversions, we must first relearn how we interpret numbers in base 10. A number is made up of digits in different columns. For the number 5978, the digit 5 is in column 3, the digit 9 is in column 2, the digit 7 is in column 1, and the digit 8 is in column 0. In base 10, we are used to saying that the 8 is in the ones column, the 7 is in the tens column, the 9 is in the hundreds column, and the 5 is in the thousands column. The key observation is that each column corresponds to the base raised to the exponent of the column number. For example, column 0 corresponds to 10 to the 0, which equals 1. Column 3 corresponds to 10 to the 3, which equals 1000. So the number 5978 in base 10 is really 5 times 10 to the 3 plus 9 times 10 to the 2 plus 7 times 10 to the 1 and 8 times 10 to the 0. We intuitively know this, but it's useful to review exactly how it works. The only thing that changes when we change the base system is the base of the exponents. That is all. So using this method, let's look at how a number in base 2 would be interpreted. 11010 base 2. Let's number our columns. Instead of the columns being ones, tens, and hundreds, the columns will correspond to powers of 2. 1s, 2s, 4s, 8s, and 16s. So this number is 1 times 16 plus 1 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1, which equals 26. Let's do one more example. 1 0 0 0 0 0 1 1 base 2. Taking a shortcut, we can ignore any columns with zeros. This number is 128 plus 2 plus 1, which equals 131 in base 10. Let's look at an example in hexadecimal, or base 16, or just hex. Before we do that, we might need a reminder for how the extra digits in hex work. This table shows you at a glance how the first 16 numbers look in decimal, binary, and hex. This table will be provided on exams. The first extra digit, A, is after 9 and has a value of 10. The last extra digit, F, has a value of 15. Let's take a look at the number in hex and convert it to decimal. 3FB base 16. Just as we did with base 2, we number our columns and then determine the power of 16 for each column. Our columns will be the 1s, the 16s, and the 256s. So the value of 3FB base 16 is 3 times 256 plus F, which is 15, times 16, plus B, which is 11, times 1, which equals 1019 in base 10. That's all there is, really. To convert into decimal, you need to number the columns, starting with the 0 on the right, multiply each digit times the base raised to the column, and add it all up. You can now convert from any base into digital. In this video,